Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. And for today's episode, I am joined by someone I've known for a really long time, and we've been threatening to make this podcast for probably like 2 or 3 years now, every time we see each other. And I finally managed to nail him down and get him to agree to spend some time with me talking about himself and the fantastic work that they do at his business. So I'm joined today by Ian Foley, who some people would know, who is the CEO of an amazing company called Equipmake. Thanks for joining me today, Ian.
Hi, Ryan.
So in the customary manner, if we could get started just by learning a little bit more about you for people that don't already know you. So where did you get started? Where did you come from?
So, well, I'm an engineer by profession. I trained in engineering at Coventry back in 1981, graduated in 85, and decided that I was a bit bored doing what I was doing, and I wanted to go Formula One racing, and I saw that active suspension was being developed, so I got myself over to where that was being developed at Cranfield, did an MSc, and I was really lucky enough to get off the job by Lotus. So I'm actually in Norfolk because I came to Lotus in 88. I joined the Formula One team in 91 on active suspension, and had a great time there for a few years, and then after that started doing my own thing basically. So yeah. So
when you were at Lotus, so you were at Lotus Formula One then. What sort of period was that?
So the Formula One team was 91 to 95. So I joined Lotus Engineering in 88, working on active suspension and active steering. And that was just a dream come true. I mean, as a 20-something engineer, I was given a Peugeot T16 rally car with active suspension, steering, braking on, and told to get the steering working. And did that for a couple of years. And then when Peter Collins took over Team Lotus in 91, I was fortunate enough to be offered a position there working for Peter Wright, doing the hardware side of the active suspension system.
And so hardware from a kind of electronics perspective, or mechanical hardware, or a bit of both?
So it's a bit of both, really. So the team was kind of very tight for money, but that was actually great for me as an engineer, because you got involved with a bit of everything. So there was myself doing the electronic hardware. So the actual electronics was developed at Cranfield. It was a hydraulic suspension system with Moog valves. So I looked after all of the hardware development. And then there's another guy who came over from engineering called Rick Townend, who did the software. So basically between Rick and I, we developed the active suspension system that raced in 92 and 93.
Rick Townend. Okay. I know him. Yes. Okay.
You know him.
Very good. So, I mean, that sort of era, I mean, active steering, active suspension, these were like really new cutting edge technologies.
Well, it was when I look at where we were at then, and the whole story, actually, I recently convinced Peter Wright to write his story, and I'd advise anybody to buy his book. It's fantastic. But Peter raced an active suspension Formula One car before the internet, mobile phones, personal computers, etc.
Yeah,
they put a computer-controlled hydraulic suspension on a Formula One car, and Nigel Mansell actually raced it. It actually ran for the first time the day Colin Chapman died, and they raced it. Now, when I joined in 88, it was still absolutely groundbreaking stuff. But, you know, we were developing active suspension and active closed loop active rear steering, or steer-by-wire cars, you know, and not just cars, we did a tank, etc. And again, we were So we were developing the software was all machine code. So you had to develop all the algorithms were handwritten in machine code for a full suspension system. I look at what our engineers do now with MATLAB Simulink and hit a button and get the code, and you think this life's easy today. You have to do all that by hand.
Yeah.
And so it was truly groundbreaking stuff in '88, and it was a kind of and Lotus was so far ahead of everybody else. It was just a fantastic place to be.
Kind of a good spell then. And you were at Lotus F1 for a few years then, or what?
Yeah, so it was 91 to 95. So I mean, unfortunately, it wasn't a great time, for Lotus. And at the end of 95, it finished. And then I went on to run myself and a guy called George Howard Chappell ran the GT program for Lotus for 3 years. So I was a race team owner and manager for 3 years.
Oh, okay. Were you in the sort of British GT and things like that?
It was actually it was called the BPR series.
BPR,
so it was the global GT series. So we turned up at the time. Lotus had been running there with Chamberlain. They had an 1100 kilo Esprit. And so George and I George and I had two of the Team Lotus mechanics, and we personally daubed a new bodywork. So we convinced Lotus, they gave us the molds. We got some pre-preg glass fiber. We took 200 kilos out of the car, convinced Alessandro Zanardi to drive, and we almost won the first race at Donington, a 4-hour race, and the gearbox broke with about 10 minutes to go. But we won our class at Silverstone later on. So we came into the series and got the weight limit, I think, started at 900 kilos, and so we were a couple of 100 kilos below everything else. And so that was quite an interesting challenge as well. Yeah,
well, I probably shouldn't tell you this, but I think I was competing against you at that sort of era. So very much my beginnings in motor racing in GT with like Marcos cars and Lister and the old Porsche, the air-cooled Porsches, so 993s and stuff. So yeah, back in the day, I didn't know that part. So you from Formula One, I mean, at that time, in that era, people might not quite understand it now because obviously F1 is quite corporate now and things, but it was bloody hard work back then. It was a very different beast to what it is now.
It was completely different, and I think one of the biggest differences was that effectively, because of the pace of development, that you were developing stuff at race meetings. So I think part of the as you say, it's now fully corporate, and by the time a car makes it to race weekend, it is fully developed, fully reliable. And actually, if a car fails during a race, it's quite a big surprise.
Yeah.
Back in those days, we were actually, I mean, I remember at Silverstone, we redesigned the suspension system at the race weekend.
Yeah.
We decided we made a mistake and we moved the accumulator from the front to the middle, replumbed it, etc. And we had one of our best results that weekend. And it was just it's a completely different environment, and I think a different type of person who did it. Really, I think
you had to be a bit mad, a bit able to deal with no sleep.
You did have to be a little bit, but I think it was a different type of person. I think Formula One now attracts a different type of engineer. There's no right and wrong about it, but it's just different now. It's not, there are a lot fewer people. Attitudes to risk were different. Yeah. Now, again, there's no right and wrong in this, but there were things were a lot riskier. There were more accidents. There were things done then, which, I mean, for example, I remember in those days there was no pit lane speed limit. Yeah. And one of our engineers, his leg had been broken by a Ferrari in the pit lane. Yeah. And the last races of the year were Japan and Australia. So, and we have very few people in the team. So the team manager came to me and said, "Look, Ian, we haven't got enough people. Can you take the front left-hand wheel off?" And I was like, "I don't know. I'll give it a go." So I was a front left, as well as the active suspension guy, and I did the pit board. For the last 2 races, I was a left-hand front wheel off man. And Johnny Herbert broke his wing on the first lap of the Australian race. So I'm standing there. I've had no training. He's standing there looking down the pit lane. And the drivers could come in as fast as they felt they could drive safely. There was no speed limit. Yeah. Stop the car and etc. So it was kind of, I really enjoyed it. It was a fantastic time, very hard work, but completely different to F1 of today. Completely different.
Yeah, a bit more edgy, I think, is the best way of.
Yeah, a bit more edgy. Yeah.
I did actually. So I never worked in Formula One, but in the GT stuff, I did get run over in the pit lane at Spa, in the bottom pits, and got hit by a car quite hard that then drove over my legs, which wouldn't happen. Hobbling about for the rest of the week. So yeah. Anyway, right. So you did GT racing for a couple of years with running the Lotus cars and BPR and all that, and then when did you what happened there? Did you stop? Was it a conscious decision or just sort of change of?
Yeah. So I kind of decided that I'd like to do my own thing, but didn't really know exactly how. And I thought, well, I've got this skill set. I can do electronic-y type stuff. I was always into. I kind of love control systems, and so started to try and build a business around that. And around the same time, when we ran our own team, we employed Jan Lammers as a driver for us. So I built a relationship with him. He started doing his own thing and said, well, actually, Ian, do you want to come and race engineer for me at weekends? And he was doing Le Mans. And this was around the time that Audi developed the first paddle shift system.
Yeah.
So we did Le Mans the first year, broke about 3 gearboxes. And I said, well, I'll tell you what, Jan, I'll develop a paddle shift system for you, which I did. That worked. It worked very well with the Judd engine, and a couple of years later, I had half the Le Mans grid had the Equipmake paddle shift system on. So I was running up and down the pit lane, and I got the contract to do the Grand Prix Masters series, and we did that. So all of a sudden, Equipmake, my one-man company, was doing all this paddle shift stuff in racing, and that's really how Equipmake kind of got started as a control systems company.
Oh, okay, so right into sort of motorsport, right at the, I guess with your heritage and history, that's where you were. So not that surprising, but for me now learning this, it is surprising that you were straight in at that kind of top level of motorsport.
I mean, everything I've done has been kind of opportunistic, I would say. That rather than having some great strategic plan and see it play out, I've seen opportunities and said, well, yeah, sure, we can do that. And I also have built up a very good network of people to support me. So I knew how to get things done. Yeah. And, so that's how it kind of started.
And then, so from that sort of early beginnings in motorsport and so transmission control and things like that, how long did it take you to start getting involved in non-motorsport activity?
Well, there's a bit in the middle where I got back into motorsport actually, which was through flywheel development.
Okay.
So I was doing the paddle shift stuff, and then as I mentioned, I used to work for Peter Wright at Team Lotus. Peter had become Max Mosley's technical advisor. And I was having a conversation one day with Peter about how to get more paddle shifts accepted into FIA series, because it was great for costs and etc. And then he happened to mention that, actually, Formula One's going to go hybrid, and which I said, oh, don't be stupid, that's not going to happen. He said, no, it's all going to happen. And I knew of a technology which had been developed by Urenco, which was part of British Nuclear Fuels, which was a composite flywheel technology.
Yeah.
And so I acquired the rights to that and went round all the Formula One teams saying, I've got this solution to hybrids and Formula One, and did a deal with Williams and started developing a hybrid, a composite. So the flywheel was effectively a composite electric motor.
Yeah.
Williams were initially a customer, and then they became a shareholder.
And so was that sort of middle 2000s, or?
So that was 2007 that started.
Yeah.
And so so that was kind of running in parallel. So Equipmake was still a kind of one-man band, which is still operating.
Yeah.
And we built up this flywheel business. And and it tested on the F1 car. It never raced, but we won the contract with Audi, and it raced and won Le Mans 3 times with Audi.
Right.
And at the same time, we had various other non-motorsport customers. One was one of the UK bus operators, and we got a contract to supply those guys, and the business got sold to GKN on the back of that. So by that point, it was about 50 people, and so I stayed with that for a couple of years afterwards. And then by then, Equipmake was developing their motors and inverters independently.
So just to kind of go back a little bit, because I think it might be interesting for people, obviously in the kind of evolution of electrification, going back, you know, in the sort of early era, sort of 1990s, we had this big challenge with battery technology. Like batteries were a significant limiting factor in terms of what you could do with a system. So people were kind of looking at lots of alternatives.
Yeah.
What was the appeal to the flywheel system, so compared to the batteries of the day?
So the key thing with the flywheel was it was the best solution for high power deep cycling. So when the power was very high compared to the amount of energy, so for a KERS application was key, where you had, say, you know, I mean, it was limited initially to 60 kilowatts, but hundreds of kilowatts for a few seconds, and you want to continuously cycle it. The flywheel was the best solution. So it was really more competing with ultracaps, but ultracaps were very sensitive to temperature. The flywheel was lighter, and at the time, batteries weren't quite there. Now, the challenge we had was during the development of that business, batteries got better and better and cheaper. So effectively, batteries have won out in all but a few niche applications.
But these hybrid things were pretty special, weren't they? In terms of, like, you know, you sort of think of flywheels. Sorry, the flywheels, the engineering in them. Just some of the outline specifications of these. There's a lot.
It's phenomenal pieces of engineering. I mean, the tip speeds are going at more than Mach 1. They have to run in a vacuum. So our flywheel was spinning at 45,000 RPM. It was a composite filament mount device running in a vacuum. One key thing was getting the bearings to last, but it was it was a phenomenal piece of technology. As I say, I kind of inherited a lot of it from Urenco, which had developed it originally, and then we further developed it for this application. So the thing that was a bit sad was, in the end, the team we built had fully developed this technology to a fantastic level where it was very reliable. It's just that the commercial applications for it were too limited.
And flywheels. There are some flywheels stuff still kicking about, but it's not like you said. It has been kind of superseded in most places by better batteries that can handle higher powers and ultracapacitors as well that can more commercial.
Absolutely, but ultracapacitors and batteries have got lifing limitations that flywheels don't. So I know there are, so there's an application where you want continuous cycling and you need a device that's going to last for 20 or 30 years and not have any aging over that time, etc. There are, and I got contacted the other day by somebody who said, I've read about this flywheel. It's exactly what I need for my application. The challenge commercially is that there are very few of those niche applications for which the flywheel is the only solution. And therefore, commercially, it's very difficult to build a business case around it.
Getting that scale in, So, but during that period, like you said, I mean, the Audi was a storming success with the flywheel technology fitted to it, and that 3 seasons of.
No, I think it raced for 4 and won the race. We certainly won. They won 3 years successively with the flywheel technology.
So and actually at that time, that was sort of hybrids were very new in everywhere, let alone in motorsport. Full stop.
Yes, absolutely.
the sort of the beginning of the hybrid era, whereas as now
Yes.
you look at Le Mans and all the top LMP cars and stuff. It's hybrids everywhere. So after the flywheel business, you said it. So presumably at that point in time, you were effectively running two companies. You had your Equipmake running, and you had the stuff with Williams going with the flywheel business. So, what happened within Equipmake? You said you had your own motors and electronics. What was going on back at base in Norfolk?
So we was part of the hybrid development. We needed to prove the system on a bus. And so Equipmake did the systems integration to get the flywheel onto the bus. So, and at that point, Equipmake was probably 3 or 4 people. So we're doing niche engineering activities. But part of that was doing all the systems integration to integrate the flywheel system with a motor onto a bus, which successfully ran, and that led to orders from that company. It led to the acquisition of the flywheel business by GKN. And then, having learned an awful lot about high performance, high speed motors, we then at Equipmake started developing motors and inverters internally at Equipmake.
And sort of skipping forwards to the present day, that's very much your sort of mainstream business now.
Yeah. So Equipmake's kind of like got two businesses in one, I'd say. We develop motors and inverters, of course. What's really, really difficult, I'm sure, as you would agree, Ryan, is that if you're a small kind of, as the time we were, say, we got to about 15 people person company, nobody really wants to be the lucky first person to specify your device on their kit.
Yep.
But what we found was there were end users who were very happy for us to provide a solution. So, for example, we've ended up supplying First Group, which is the biggest bus operator in the UK, with repower solutions for complete vehicles.
Yeah.
So we did systems integration, basically to sell our own product to the end customer.
Right.
So we've ended up now where, if we fast forward to today, we've got a side of the business that does very specialist motors and inverters for specialist applications, like, for example, we're developing the electric motor, which will be on the globally, we believe the first fully certified, fully commercial aircraft will have an Equipmake motor that will be certified by EASA. We're developing motors and inverters for rocket fuel pumps for a company called Gilmore Space, so a space rocket application in Australia.
Okay.
And we're developing wave energy, motors and inverters for wave energy that, again, have very, very specific technical requirements. So an off-the-shelf product won't meet it. So we've got these. So people have come to us because they need something which is you can't buy an off-the-shelf solution for.
Yeah.
And we have a business developing that and manufacturing those and selling those in production. And alongside that, we are still doing vehicle projects. So, either we're repowering some vehicles at the moment, or we supply. For instance, the second biggest fire truck manufacturer in the US, Rev Group, has a hybrid system we've developed. We supply Textron with airside de-icing vehicle complete electrification system. And again, these tend to be systems where you can't just go and get an off-the-shelf solution.
Yeah.
And so there's something about them which is, I say people come to, on the vehicle side, people come to us for the heavy-duty, difficult stuff.
Yeah.
And then on the motors and inverters side, there are applications which have quite demanding technical requirements.
Yeah.
And we've attracted quite a few of those. And that's kind of where the business is at the moment.
I mean, that the heavy-duty sort of difficult niches, a lot of people, obviously the heavy-duty market is trucks that you see on the road and products that people are familiar with, but then there's a vast array of specialist companies behind that who are making equipment for, any kind of job that you can think of. I remember there was a company I came across in the US who made machines for polishing ice rinks, and people would know who that is, but they're a huge company. You think you're polishing an ice rink, how's that a business? But de-icing stuff and specialist fire trucks and all sorts. Yeah, it's a huge the niches for special purpose vehicles it's massive, isn't it?
That's it, and that's why it suits a company like ours, because there's huge competition at the moment, particularly from China. But most large companies need large volumes. So for volume product, there's bigger competitors than us, and we're not competing directly with those guys. But you go to these niches, and often there's a good reason why they can't just go and buy one of those systems. There's something that they need doing a certain way, and generally, because we're kind of we're at the end of 100 years of development of diesel and conventional systems.
Yeah,
these are products which there's a whole supply chain, and there's a network of people out there can provide you a diesel gearbox solution for.
Yeah.
But in the world of electrification, there's not that many people who can do the full integration for something which is a little bit special.
Yeah.
And that's kind of the niche that we're filling at the moment.
Because that's something that people, I think, might forget, that in the heavy duty market for these sort of lower volume vehicles, actually there's been an industry. If you make a special machine for polishing ice or blowing snow or whatever, you don't make your own engines and transmissions and axles and things. There's a whole supply chain of specialists who make diesel engines for that sort of thing, and axles and transmissions, and that's all developing now for the electric or for hybrid systems in a similar kind of way. So do you see yourself in that mix as potential?
Yeah, no, absolutely. And I think one of the key things we've discovered is that in a lot of cases, people don't actually understand the exact specification they require. So, for example, if you want to make a truck of a certain weight, if you go and buy this Cummins engine and this Allison transmission, this axle, it will just work.
Yeah.
And people don't necessarily have... So once you get to an electric solution, the customer often can't give you a full set of requirements, but they expect the thing to work.
Yes.
So as an example, one of the vehicles we worked at was parked somewhere on the grass. It sunk into the grass, and the vehicle was able to get itself out of that situation. But the comment made back to me was, well, it only just managed it. And I said to them, well, where is it in your specification? It specifies the torque required. So it's effectively like a curb or a curb type application, because a conventional diesel and torque converter gearbox because it's been developed over 50, 60 years, and it's kind of that those requirements are automatically met by that solution.
Yeah.
When you come to an electrification solution, people don't know they need to ask for it.
Yeah.
So there's this kind of, we often come up against that, but that's where having the ability to do the full integration, and we can always find that solution, because the customer needs a solution. I think it's no good telling the customer he's wrong. He's like, well, I've got this vehicle, it doesn't work properly, and I need you to fix it.
Yeah.
And we need to fix it. So our approach is to, and there's a whole load of those issues. And if you fast forward, or the other classic one at the moment actually is charging systems.
Right.
There's a charging standard called CCS2, but it's not fully developed. So you can often have a CCS2 charger, a CCS2 system on your vehicle, and it doesn't work. And we have to go in and tweak timings of things to get it working.
Yeah.
Now, what will happen is that standard will get developed over the next 10 years. So in 10 or 15 years' time, these problems will all be solved.
Yeah.
But they're not solved today.
No. Well, because people like you are working on solving them. So... yeah, they don't just solve themselves. Yeah.
And people often say to me, the comment I often get is, well, how come cars just work? And I say, well, they don't. I mean, I've got a Mercedes EQS. It's often I'll go to a charger, plug it in, and 2 minutes later it'll trip out.
Yeah.
And then I'll end up going to the next charger, plugging it in, and it works. And so the mainstream systems aren't fully sorted yet, and they will get there over time.
Do you think as well, part of it with electrification, and especially in the sector that you're in, so the traditional heavy duty market, everything would be sort of over engineered to an extent, because when you're launching a passenger car, you've got lots of upfront development and testing, and you kind of can refine it to get the piece cost down. In the heavy duty side, you're limited in terms of the upfront investment and development. So you just always end up over-engineering things.
Yeah.
But a lot of the systems on the vehicle then wouldn't be very efficient, basically. So you end up with things like fire trucks where some example like cooling fans are massively overspec'd on diesel
Yeah.
fire trucks and buses. Actually, on that was something that I used to do a bit of, and it wasn't kind of like it wasn't a problem because that inefficiency was just sort of lost in the system, and everyone was the same level of inefficiency. But with an electrified product, there's like more. I'm probably going to end up with hate mail from loads of diesel engineers now, but there's like this sort of level of finesse that you don't really have to think. You wouldn't want to waste that energy. You could just over-engineer everything. You could have a battery that was loads bigger and a motors and drives that were loads bigger than you actually needed. But you just wouldn't, because you don't want to waste the money or because these things are expensive. You're trying to get the system costs down and you want the efficiency because do you think that sort of mindset is more changed towards more of an efficiency mindset than it used to be?
So I think you're absolutely right. I think if you look at volumes, automotive, people are developing, I think the car market is whatever it is, 60 million units a year, and each car manufacturer will be developing a product that does make millions a year. The HGV market is 3 million units a year. Then you get down to the bus market, as you say, is, from memory, it's 300,000 units a year, of which 200,000 are in China.
Yeah.
So you can say, so an individual manufacturer is making hundreds or thousands, so there is not the budget to do the development. And to a certain extent, therefore, what you shift from is expenditure gets shifted from pre-sale development to support.
Yeah.
So most bus operators expect buses to go wrong. I think a general contract for a bus manufacturer is you've got to have 98% availability. Well, 98% availability means for 6 days a year it doesn't work.
Yeah.
If that happened to your car, you'd be pretty upset.
Yeah.
So there's an expectation that these things I mean, yes, they get a harder time, but they are less well developed because the budget isn't, the business case isn't there to have the upfront development.
Yeah.
And so to a degree, I agree with you. That means if you can, there will be a level of over engineering. Now, and as you say, with electrification, there's more of a focus on efficiency than there was with in the diesel era, definitely. Yeah.
A lot of the costs kind of, because something that I would often hear, was like, I could buy a whole car for that,
Yep.
And it's like, well, yeah, fine, go and buy a car, do that. But the like even with a diesel engine, if you look at the cost of a diesel engine that's fitted to a bus, for example, out the factory, you could literally buy a car for the cost of that diesel engine. So that sort of, but it's not that the diesel engine manufacturer is making loads more money than the car guy. It's just that it's kind of over. Everything has to be that bit more sort of over the top because you can't spend the upfront money to engineer it down to a cost.
Absolutely, and the volumes are less. I mean, as you say, that's why it's kind of interesting looking at the accounts of various businesses to see, who makes the most money. And basically, I mean, I guess we do engineering because we love it. It's not because we want to get rich. So we look at, you look at the kind of money that a Facebook or a Microsoft makes, and it's it's significantly higher. So I think one of the marvels of engineering through the late 20th century is that cars are the price and the quality they are is phenomenal.
Yeah.
I mean, I think you're a bit younger than me, but when I was a lad, I remember my dad buying a Morris Marina in 1974, and the first thing he did was get underneath it and underseal the underneath, so it lasted more than a year. And after 3 years, all the wings were bubbling away. And if you bought a car in the 70s, then in the middle of winter, you wouldn't expect it to start. You kind of have to get, you'd have to learn how to use a choke properly, etc. And and certainly, I think my first car was a 10-year-old Mini, where a rite of passage was learning how to replace a subframe, weld, and take an engine out and replace big end bearings. That was part of what you did on a 10-year-old car with 50,000 miles on. These days, a car, I mean, I don't know what the cheapest car you could buy now. It's probably 15,000, 20,000 pounds or something. And the quality is phenomenal.
Yeah.
And that's through continuous engineering and high volume over 40 years of development. And it's a marvel of modern engineering, I think. The older cars that were written off because of rust and corrosion and sort of excessive mechanical problems, like the mechanical issues by the by in general, although there's some pretty big mechanical
problems that it can still occur. But electronics, so much more electronics in cars that go wrong, and
Yes.
not being able to get a replacement electronic ECU or part, is an often cause of writing a vehicle off now. So it's a different, but you don't have to. I mean, I did. Probably not everyone, it wasn't a rite of passage when I was kind of starting to drive, but personally, because I think I was tight or poor or a bit of both, I was sort of on my back welding biscuit tins onto the sills of my Ford Orion, I think it was at the time, or the old Volkswagen Polo that I had, which was dropping to bits. Yeah, you wouldn't do that now. And I think my wife would kill me if I even suggested putting our kids in cars like that.
One thing I think is a game changer. I believe that the life of electric vehicles is going to be significantly longer. And now part of this is I don't have data to back this up. The only bit of data I've got is I actually bought a Tesla Model S in 2014, and I got rid of it after 9 years. Not because it was going wrong, but because I was worried that it would. So by that time, it got 90,000 miles on. It had the same battery, no perceived loss of mileage, and no rattles or creaks or anything.
Yeah.
And you think, well, this is just going to carry on going. And I think it's the same for commercial vehicles. So I think that, and also from a performance point of view. So any diesel car I've had, if I had it for, it might have been 7 years, not 9 years, 7 or 9 years, and you get 100,000 miles on, it's generally rattly. It's lost some performance, etc. With the EV, it lost no performance. The performance was fantastic to begin with, and I probably should have just kept hold of it, and it would have been running now. So I think that, and certainly if you look at commercial vehicles, I believe that the longevity and running costs of commercial vehicles will be a lot longer. Electric commercial vehicles will be a lot longer. And this could be a bit of a game changer for the industry.
Yeah, I wonder. Just think about buses for a moment. So, obviously, that's a big part of what you guys do. I used to jokingly say to people, obviously, you've come from motorsport, and people always go, "Oh yeah, motorsport's great, proving ground for technology and this, that, and the other." I'm like, yeah, if you want to really test a part, put it on a bus.
No, absolutely. Motorsport's been a huge part of my life. I love it. But what you just said, I always say that's just marketing. At the end of the day, because the big thing with motorsport is the thing that I would lobby for in motorsport is people should have proper cost constraints, because the really challenging thing in engineering is doing things for cost. And compared with the real world, Formula One might say that there's budget caps. Compared to the real world, these are proper caps. So what you have is an unlimited engineering budget, and a thing that needs to last, even if you take Le Mans 24 hours.
Yeah.
But as you say, if you're running, we've delivered buses systems into the field. They run 15 hours a day, 350 odd days a year.
Yeah.
And they've got to run every day, and they get a hard time.
And particularly, actually just think about the comment on the electrified stuff, because a lot of the issues on a bus are sort of inherent in the design. So you hang the engine out the back, cantilevered behind the back axle. You've got all that weight bashing around over speed bumps and through potholes and whatnot. And it's actually, the whole design of it is awful. Like from the beginning, of anything that's on the engine or the drivetrain at the back is going to have a really hard life because of where it is. But an electric powertrain can be sort of much better packaged into the vehicle. So the components are not necessarily, you're not going to see the extremes of temperature and pressure and stuff that they would have in a typical setup. You've got things because the engine's at the back, other than, I don't know when the last bus was that went away from a front, the cooling system being on the front, but the rear engine, rear cooling pack. But you could completely change the design of a bus, couldn't you, around an electric powertrain?
Yeah, absolutely. And there's been a few goes at this. And I think that will happen. It's already happening. So yeah, definitely.
What do you see? So in terms of Equipmake and where you guys are at today, you mentioned so you got your repowering business and the aftermarket stuff you're doing, but then you sort of very quickly glanced through some quite exciting sounding programs for it's not rocket science, but it is rocket science. So can you tell us a bit more about some of the sort of electric motor programs and what's special about your motor and inverter technology?
Yeah. So I think we've been quite fortunate in that, we have won projects like the motor and inverter for rocket fuel pumps. So, and on that project, what was really interesting with that one is that's a low Earth orbit satellite launching rocket. So it starts off at atmospheric pressure. 2 minutes later, it's in a vacuum, and then it goes bang and it's all over. Now, with power electronics, if you run them in a vacuum, you get a thing called partial discharge. So how do you cope with that? And our solution was to maintain atmospheric pressure within the inverter, so we don't have to worry about that. That means that in a vacuum, it's a pressure vessel with 14 psi trying to push out. So we developed a circular inverter with a carbon fiber case because it has to be light, and it has to be sealed. So that was a really interesting technical challenge to solve that particular problem. So we've developed technology around an architecture called a spoke motor, and that's where the magnets are like the spokes of a wheel, and we've developed a manufacturing technology around that. But what we always say to customers is we're kind of agnostic, and we will look at the application and try and come up with the optimum design for that application. So the rocket fuel pump was a spoke motor, but the aerospace motor is a Halbach array surface permanent magnet motor.
Okay.
Because the rocket fuel motor is 20,000 RPM, but the one for the aircraft is driving a propeller directly. So it's a maximum speed of about 2,500 RPM. So you want the very highest torque density, and cost isn't the main driver. So that's led us to a surface permanent magnet Halbach array. And in the bus motor, cost is an issue. But the optimum motor for that was what I would call a conventional interior permanent magnet motor. So we have, and we've ended up with, if we look at our bus motor, which is 3,500 Newton meters and 200 kilowatts continuous, it's 200 kilograms, and it is very, very competitive in terms of weight. So we don't have a particular motor technology and we say we've got the best mousetrap for everything. We look at the application, develop the motor for that application.
Because that actually is quite different to most other suppliers in the space. You tend to get people who've got one speciality, hairpin wound machines or Halbach array machines. So how do you deal with that sort of? I mean, that's a lot of technical complexity, but across all those different technologies. How do you deal with that?
Yeah, that's a very good question. Hairpin's an interesting one. So we haven't done a hairpin yet. So all of our motors have tended to be what's called concentrated wound. So we have an individual tooth and wind the wire around that, which actually means for lowish volume is very, very easy to be flexible amongst different designs.
Yeah.
Hairpin is much less flexible, and to get reliability at volume, it really requires quite high volume.
Yeah.
So we often have the discussion with, and also people often in engineering, things that sound reasonable and rational end up being false, I find, when you look into the detail.
Yeah.
So you often get people saying, well, hairpin must be best because you've got these big square conductors which you get a better copper fill of your area, so therefore it must be better. But if you look at a hairpin, you've got a big end winding which is doing no work, but is producing losses.
Yeah.
So when you look at the net, often, although a distributed wound, you get less copper fill, you've got much lower end winding copper.
Yeah.
So often you find that this nets out.
Yeah.
So people then say, but why is all these automotive engines hairpin? And I say, well, I don't know. You tell me.
Yeah.
Now, the other thing with automotive is automotive is a special case because automotive is designed around a particular drive cycle. It was very, very, very low power. So it takes about 30 kilowatts to drive a car at 70 miles an hour. And the average power of the drive cycle, the WLTP drive cycle, I can't remember the exact number, but it's a lot less than 30 kilowatts. But you often want about 200 kilowatts peak for the acceleration.
Yeah.
So you end up with something that needs to be super efficient and smooth at very low power. And you're not really bothered about the losses at high power. A lot of what we do is either something like the the pump motor is a fixed speed, or we're doing high power stuff. So it depends on the duty cycle.
Yeah.
So we've ended up, if we were to design an automotive motor, it would probably be a distributed wound motor. It would probably be a hairpin motor. It's just that most of the things we've done haven't been that.
Yeah.
But I think there are people who make assumptions, and there's a kind of a trend or a fashion to saying, well, if the automotive are doing hairpins, it must be the best for everything. And we would argue against that.
So one of the other things that actually possibly connected, but a downside of the hairpin machines being higher speed and higher switching frequencies. And then there's been a bit of a trend recently towards more higher and higher motor speeds in automotive. So you've got 20,000 plus RPM motors in new cars from big OEMs, Tesla, etc. Where are you on the speed race? Are you?
Yeah. So well, the interesting thing is in terms of the losses, because as you say, hairpins got big, thick conductors, so they're not very good at high frequency. But if you multiply the speed by 4, but you reduce the pole count, you will end up with the same frequency.
Yeah.
So I'm kind of guessing that the high-speed hairpin motors must be quite low pole count. We end up with most of our motors, we end up with quite a high pole count, which means that high-speed losses become more of an issue. Now, in terms of overall speed, I think it's really, really interesting because, again, if I look at, and I'm getting a bit old now, if I look at my experience of cars from the 1970s onwards, you had a whole in the 70s, you had a whole range of types of engine, flat 4 air cooled, different speeds, you had different chassis, etc. And over 40 years, the optimum emerges, and all car engines do. Despite the fact that Formula 1's shown you can make effective engines doing 20,000 RPM. Why is a car engine maximum of 8,000 and runs at 3,000? Because that's the optimum for cost, NVH, etc., etc., etc. So you kind of say, right, well, what's the optimum for a motor? And I don't know the answer. Well, one thing is, as speed of the motor goes up, the gearbox gets heavier and heavier and more complex. So you trade complexity of gearbox with complexity of motor. Once you get above 30,000 RPM, bearings become a bit more difficult. So we've actually done a motor which is 30. So we chose 30,000 RPM as right for our latest technology. We'll do a 30,000 RPM motor, but it's really throwing a dart at a board. I don't know where it'll end up. My guess would be it's going to be somewhere between 20 and 30,000 RPM for a car type application. Now, what's really interesting in a heavy duty application and aerospace is we ended up deleting the gearbox. So we went for direct drive, which gives you a bigger and heavier motor. However, you've got much less complexity. And what was really interesting from the industry, when we went to the industry and said, right, what we're doing is we're deleting the gearbox, everyone said, oh, thank God for that. You wouldn't imagine how many problems gearboxes give us.
Right. Okay. Yeah.
So I'm actually with Elon, but I don't know if love him or loathe him, Elon Musk puts forward, he's got like a 5-step strategy. And one of his things is that he said engineers spend lots of time optimizing things that should just be deleted. And I tend to agree with him. So we've where we can, we try and delete gearboxes.
I mean, gearboxes, which seem simple on the face of it, that's another one of those components that are incredibly hard to engineer a reliable transmission, even at low, sort of single digit thousands of RPM, let alone 20, 30,000 RPM reduction drives. It's a horrendous level of complexity. So looking forward then to the future, where do you see Equipmake going? Like what are the sort of big programs coming up, or the new technologies, or what's got you excited about the next kind of year or so?
So what we're trying to do here, the vision is that we will, at the moment, our production levels are in the hundreds. So the vision is with some of the projects we've mentioned, we'll get to thousands of motors and inverters a year. So our production capability will be manufacturing lots of thousands per year of motors and inverters for these higher value projects that I've mentioned, like rockets and wave energy, etc.
Yeah.
And then in parallel with that, we've got the niche vehicle stuff, which is building as well. And from a technology point of view, we've been developing silicon carbide inverters for over 10 years. So we try and kind of keep at the cutting edge. And the great thing about projects like space rocket motors, etc., is they keep pushing us technologically. So that keeps the engineers here busy and engaged. And hopefully as that technology then feeds down to the other projects, we're actually keeping, hopefully, at the cutting edge of power electronics and motor technology.
And do you see, so, sort of space is one thing and the renewables is another, but do you see your sort of products getting engineered into more land vehicles, sort of in off-highway and things like that?
No, absolutely. I mean, we were very fortunate that in a couple of months ago, we announced a big investment from Caterpillar into the business. So we have, it's actually a government-funded project with Perkins, which is part of Caterpillar, where we're designing a motor inverter into all their gensets. So we've had a relationship with Caterpillar for well over a year, and that led to them making an investment in the business. So I think off-highway is a huge opportunity for us, and hopefully with that relationship, and also in kind of around the same time as that, we announced a contract with JCB as well, where developing bespoke product for those guys. So I think the off-highway side is the latest to the electrification party. It's probably more likely to be hybrid than full electric, but again, it depends on the application. And because we've had on the vehicle side, our focus has ended up being on heavy duty side. A lot of what we're doing is directly relevant. So I think, off highway is potentially a big opportunity for us.
And that actually, so one last thing. So where we are right now, I've been doing these podcasts for a good few years now, and in the kind of EV and electrification space for a long time. But it's a sort of funny time at the moment because we're seeing lots of sort of talk of electric vehicles being sort of I wouldn't say dead, but like the demand not being there. And I just, there's various reasons I disagree with a lot of that. It's more to do with high interest rates and people not being able to afford expensive cars. But where we're at right now, looking forwards, like what do you see coming in terms of powertrain? Do you think by 2030 every truck and bus will be electric, or do you think there's going to be lots of hybrids, or same in off highway? Is it one or the other, or both, or neither, like hydrogen? where are we going? What's your sort of
So I would disagree. It's kind of interesting when you look at the noise, then look at the facts. But I think I'm right in saying, but you may know more than me on this, that if I look at data from SMMT, etc., that there's still significant growth in electric car sales. It's just that the growth isn't as high as was predicted. Yeah. So I see the period we're in now as very much like just after the internet boom. You had the hype and the boom. Then there was a financial crash in internet stocks, and there were people saying, there were articles in 2001 saying, the internet's too slow and too expensive and people are switching off. And we're in that kind of phase of electrification where all the time it was growing, and then you get the reality happening. And I think we're in that phase at the moment with electrification. Electrification is still growing. It's becoming more competitive. The crucial thing, particularly for commercial vehicles, is the business case.
Right.
And if you look at electric buses now, if you look over their lifetime, once electrification is cheaper than diesel over the lifetime, there's no reason not to do it, and therefore it's going to happen. And I think full electrification will happen quicker than people think. But I agree with you, it doesn't suit everything, so there will be a mix between hybrid and full electric.
I guess, the business case, that's for passenger cars, there's a bit more than just the business case, and there's lots of pushes and pulls, but for trucks and off highway, it's all about the numbers at the end of the day. Can you make it, unless it's a hard and fast rule of I have to have an electric vehicle to operate in this city, what's the best commercially for me? It is interesting now that the cost of sort of new electric trucks from the bigger OEMs, and there's been some quite big studies with Tesla trucks done in the US where they've been used for a long period of time, and like at SAE World Congress earlier this year, there was some discussion around that, and the results were really surprising in terms of just actually how much better. And there were some predictions there about, if you're not using fully electric trucks for this kind of duty cycle, then basically you're going to be out of business in sort of 5 or 6 years time, which I thought was really quite strong, and it was surprising duty cycles, because it was actually things like long haul where you would think that an electric truck actually wouldn't be that good, but the results were sort of saying the opposite. So yeah, interesting. So yeah, I think we're still at a very interesting time, aren't we? In terms of the sort of reports of the death of electrification are very much overstated.
No, but I think, do you think this is normal with any new technology? You always go through these cycles, and you get things like, the classic one where Kodak were one of the earliest investors in digital cameras, and put it on a shelf and carried on making film. And so the incumbents will always carry on, with the thing that is making the money at the moment, and the incumbents tend to be the last ones to see what's happening. So to me, that's normal. So the news flow at the moment is kind of what you'd expect. If you look at the facts behind the news flow, it looks like we're continuing on this S-curve of adoption. And, it'll probably be, I think by 10 years' time, when you look at the quality and cost of electric cars coming out of China, once these, I remember when I bought the Tesla in 2014, so it's ages ago, no, 10 years ago. And I was having a discussion with a senior industry executive who said to me, we don't think people want electric cars. We think they're being forced on them by governments. And I said, well, I've just bought one, and I'll have to disagree with you. And I said, this is in 2015 I bought the Tesla. I said to him, in every single way, apart from price and range, they are so much nicer to live with that when price and range is sorted, everyone will want one. Now, I think we're getting to the point now where price and range is sorted.
Yeah, definitely.
So I think and then I had a discussion with another person last year who said, oh yeah, but I love the roar of my V8. I said, okay, you do, but we're talking about the distribution of people here. I mean, my wife's got electric cars. She doesn't care about the roar of a V8. She loves it. So if you talk about the majority of people who aren't car enthusiasts, they want something to get in every day to take them from A to B. That when price and range was sorted in every other way, they're so much easier to live with that everyone will want one. And so I think that will, by 5 years from now, I think that 90% of new car sales will be electric.
And one last question. So we could go on all day, but I'm mindful I've taken up loads of your time already. So, but you touched on it, and I can't let us close without just asking, because you mentioned about China. And I know, we've spoken before, and you had some really interesting kind of views and comments on China. So is China going to destroy the US and European car industry, and we'll all be driving Chinese cars in a few years? Threat or opportunity? How do you see that playing out?
So a bit of both. I don't think people in the West have fully got their head around how far ahead China is. And I was astonished when I went back out there a year and a half ago. It took me about a week when I got back to process what I had witnessed. And Jim Foley of Ford said, it was only when he went to China to see for himself, he went back and said to his team, we have an existential threat. So what's really interesting to me is, and I know you've been to China recently, what's really interesting is you read articles in the press, you see it on the TV, and you form an opinion. When I went out to see for myself, I came back astonished at, in a lot of ways, how far ahead they were, and also the price that they were manufacturing for. And the fact that it's a mistake to think, for people who say, oh, it's a communist government, they're being told to buy. That's a mistake. What the Chinese have done is created a super competitive economy. It's dog eat dog. And what's emerging from that is very good technology, with very good manufacturing technology. And so from a Equipmake point of view, we are now, we are purchasing certain components, such as batteries, directly from China because of the price and quality is something we're not doing ourselves. and we are selectively working out which what we get direct from China, what we do ourselves. So it's a huge opportunity and threat. But I think that a lot of people in Europe and America do not understand the level that China are at. And like I say, the really interesting thing is Jim Foley going public and saying that as well was really interesting.
Yeah, and it's not. I got sort of mixed views on it, but I mean, the OEMs and actually Western companies have sort of created their own sort of downfall in that it's not about cheap labor anymore. It probably was, but when I was in China, I was standing in a plant using the best automation, robotic production systems, really fantastic quality control. It wasn't just 6-7 years ago, it was a lot of manual labor. It's not now. Actually, the thing that they've taken very seriously is the need to make stuff.
Yes.
And they take it really seriously, and it's very highly prized, and actually creating value, making things is really important. Yes. And the production technology and how you make it is really important, and they get it there. Whereas I think in the UK, it's maybe the oddballs like me and you that get, you said you were passionate about control systems earlier, and I love my, whereas it's much more like in China, I think they get it much more, like as a country, they're not kind of, when you say to people that you're an engineer in China, they don't automatically ask you if you can repair their washing machine. It's
no, absolutely. So I think it's both a threat and an opportunity, but firstly, people need to understand where they are and get rid of some of these biases that either, well, it's only because of communist governments forcing people to buy them, or the quality is no good. No, the quality, and there's a whole range of companies in China, but they make the same parts, make excellent quality stuff at very low cost. Engineering costs now, I mean, we've looked at doing things directly in China. Engineering costs, labor costs are similar to the UK. There's not, as you say, it's not about low labor cost. They are better at manufacturing, and they've got a huge market. I mean, at the end of the day, we've got a home market of total of 50 million people. America got an advantage in a lot of areas because they have 250 million people, and they've got billions in China. Yeah. So they've got a starting point of
scale.
Now, for us as Equipmake, well, the great thing is for us, thousands is a massive number. Yeah. My ambition, you said, where's Equipmake going to be? And I said, a few years' time, we'll be making thousands a year. Yeah. They don't get out of bed for thousands a year. They're hundreds of thousands a year. So we've got this, we can exist in this space where, they need to carry on manufacturing at massive scale, but they are just now starting to export at massive scale, and it's just starting now, and it's going to hit the West like a hammer, and hopefully people wake up and respond to it. But I don't think people realize it's coming.
I guess we're already, the bus industry the last couple of weeks is feeling it in the UK, potential downsizing, and a lot of that's to do with sort of Chinese products coming in.
It is, and one thing which I probably shouldn't get into politics on this, but one thing which I think is rather crazy is that UK subsidies go directly to China for vehicles when no other country in the world would do that. So I think that's a bit crazy. But as you say, the UK bus industry, I think, is feeling the pinch, and the other industries will as well. I think the German car industry has to be worried about it. Yeah, the Americans are, but again, if you look historically, tariffs are a temporary solution. Yeah, and people need to improve and compete properly. History shown tariffs aren't a solution. Competing effectively is the solution.
The countries, economically, countries that have historically had high tariffs tend to be the ones that are less developed in the long run.
Absolutely.
Plays it out. So, great. So we've done that question. I'm going to hold myself back and say we'll finish there now, because otherwise we will be going all day long. But fantastic to talk to you, Ian. Thank you so much for taking the time out to do this.
No, thanks a lot, Ryan. I enjoyed it.
Brilliant.